Naming acids is going to be the topic of this lesson, and we're going to specifically look at naming two different types of acids. Binary acids, typically made of just two elements, hydrogen and one other, or oxyacids, also called oxoacids. We've already named ionic compounds, we've already named molecular compounds, and now we've got one final set of rules, or really two sets of rules, for naming these two different types of acids. So that's going to really be four different sets of rules for naming compounds, and the big thing is you got to figure out which of these four types of compounds you've got, and then use the appropriate set of rules to name that compound. Now, this lesson is part of my general chemistry playlist. It's brand new, and I'm releasing these lessons weekly throughout the school year. So if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. Let's get into this. All right, so we're going to start with binary acids. And if you look at that word binary, think of the word two, just like when we saw binary molecular compounds. And in this case, your binary acids, almost all of them are made of just two elements, and one of them is always hydrogen. So, and it doesn't have to be just one hydrogen though, as we see. So, but one of the elements will be hydrogen, and then typically one other. Now, there's an exception to that, like HCN is considered a binary acid, and it's got three elements, but it's not what you're typically usually going to see in this case. So, your typical binary acids, HCl is the most famous acid. If you thought it was LSD, you're wrong, and that says something about you now that I see you. But it's HCl. That is the most famous acid of all time. It's in your swimming pool. It's the one you pour in your swimming pool. It's in your stomach. It's in your chemistry lab. It's all over the place, and you probably already know its name, which is really convenient for our purposes here. So because this is hydrochloric acid. So for a binary acid, you always start off with hydro and end with ic. And then what goes in the middle is just indicative of what that other element is. And so if I was going to name these two as well, I would just set up the hydro and the ic and just figure out what goes in the middle. Now, one thing you should know here is that all three of these are also molecular compounds. They're made of only nonmetals. Hydrogen's a nonmetal, so is chlorine. Hydrogen and sulfur are nonmetals. Hydrogen and selenium are nonmetals. And so the question is, well, can I name them as a molecular compound too? Maybe. And so the way this works, you're going to name them as an acid like this only when they're dissolved in water. That's actually when it's proper. Otherwise, you'd probably name them as molecular compounds. And so here I'm going to put this lovely aqueous in there. And some professors and textbooks don't make a big deal of this, and some like make a really big deal. And you got to see, am I talking about, HCl gas, or am I talking about HCl aqueous? HCl gas is just hydrogen chloride, whereas HCl aqueous is hydrochloric acid. So really just want to take the cue from your particular instructor to figure out how important that distinction is for you. But this is what's really proper, which is why I'm presenting it that way. And so these next two, we're going to put hydro, leave some room, and then ic, acid for both of them. So hydro, leave some room, ic, acid. And so in the case of sulfur, we just actually say sulfur. So this is going to be hydrosulfuric acid. And then here for selenium, it's hydroselenic acid. And I just wanted to give you a couple examples. So again, hydro something ic acid. Oh, and I forgot the word acid up here. Look at that. That's terrible. That's part of it. Hydro something ic acid. Cool. And so binary acids are not so bad, and especially if you can always relate back to one that you know the name of, in all likelihood HCl, hydrochloric acid, life is good. So those are your binary acids. The oxoacids, or oxyacids as they're called, are going to be a little more of a pain in the butt. However, if you know the corresponding names to the oxyanions they are the acid of, it'll make your life a little easier. So let's do a little review. I need a little bit of room here, so we're going to get rid of this. It's served its purpose. All right, back in the naming ionic compounds lesson, we talked about you needing to memorize all the polyatomic ions, and it's going to come back up in this lesson as well for naming oxyacids. And so here's SO3 2-, that's the sulfite ion. Here's SO4 2-, that's the sulfate ion. And if you know the names of all those polyatomic ions, it's going to make naming the corresponding oxyacids a little bit easier. Now notice these are both -2 in charge, and that's why we're going to put two hydrogens, which we say is in the +1 oxidation state. That's why there's two needed. For polyatomic ions that are -1, you need just one hydrogen. For polyatomic ions that are -3, you'd need 3 hydrogens, so on and so forth. But these guys are -2, so they need 2 hydrogens. And the way this works, if you look at, we'll start with the sulfate, the bottom one first. What you're going to want to do is turn that 8 into an ic. So, and it turns out also, instead of just sulf, it is sulfur. And so this is sulfuric acid. And so the corresponding ate in the oxyanion name becomes an ick in the oxyacid name. So I like to say that I ate something disgusting and said ick. So kind of associate the ate with the ick. And it works that way with all the different polyatomic ions. When there's two different versions, so the polyatomic ion that's named with the AT ending, the corresponding oxyacid is always going to be named with an ick ending instead. Also note that there's no hydro on the front of this. That hydro prefix is reserved exclusively for the binary acids, not the oxyacids, but this makes it confusing. It also makes it really easy to put some really good wrong answer choices there, because notice the difference between hydrosulfuric and sulfuric acid. Hydrosulfuric is binary, it's just H's and S. So whereas sulfuric acid is an oxyacid and there's oxygen in there as well. Okay, so now what do we do if we got the corresponding oxyacid of the sulfite ion? Well, the ite is going to become an us, an OUS. And so in this case, we've got sulfurous acid. And you could get really cheesy right here, and I typically do, and say that I ate something disgusting and said ick, so ate, ick, and then I got appendicite us, or something stupid like that. Anything that helps you remember, great, fantastic. So, but if you know your polyatomic ions, life is good. So if you look at like NO3 minus, that's nitrate ion. And so HNO3 is nitric acid, whereas the NO2 minus ion is the nitrite ion. So an HNO2 is nitrous acid. And so I wanted to point that out because it's not just, you can't just like memorize the number of oxygens and be like, well, 4 oxygens means 8 and 3 means ite. And 4 means ick and 3 means us. Because with nitrogen, it's actually 3 and 2, not 4 and 3. And so you got to know those polyatomic ion names at the end of the day. And you definitely got to know these as well. And if you know one, it makes it easy just to translate it into the other. And so I, again, highly recommend you memorize those polyatomic ion names. And then you'll be able to translate them right into the corresponding oxyacid names as well. Now, we have one problem here, and that one problem is for chlorine, bromine, and iodine. They don't have just 2 different oxyacids, they have 4 of them, which is going to be a problem. So, but I'm gonna need some room here. All right, we're gonna start by looking at the corresponding oxyanions for chlorine instead, and they're ClO minus, ClO2 minus, ClO3 minus, and ClO4 minus. And for the 2 in the middle, that's where we just get the ite and the ate being used. So ClO2 minus is the chlorite ion, ClO3 minus is the chlorate ion. And so then, well, they're like, well, now we have 2 more. What do we do? So, well, in this case, with the ClO4 minus, we have to look and say, okay, well, how do I let students know that we have something with more oxygen atoms than even chlorate ion? And technically, it's for something that has a higher oxidation state for chlorine than in the chlorate ion. So, but we don't know what oxidation states yet are, but we'll talk about those in chapter 4. So for me, I'm just going to say that something that has more oxygens than the chlorate ion. So if you think about this, you know, let's say you feed a kid a ton of sugar, you feed them soda and cookies and stuff, and then you send them home with their uncle and their aunt because you've been watching your brother's kids, and you send them home and they're going to be hyper. And hyper here is short for hyperactive. And so in this case, that turns out that's the prefix we're going to use here for the chlorate ion here. We're going to add on to chlorate to describe this guy. And so we'd say hyperchlorate, except they decided just to say perchlorate. I don't know why they dropped that part of it, but they did. And this is the perchlorate ion. But notice it still ends with the ATE ending. So then we had to, say that this guy's got fewer oxygens than the chlorite ion, and they had to come up with a prefix for that as well. So, and think about when you have, so we want to say it has a lower number of oxygens. And technically, again, it comes down to a lower oxidation state for chlorine. And so when you have low blood sugar, not diabetes, but low blood sugar, but you got to eat meals at regular intervals, you are hypoglycemic. So in hypoglycemic means low blood sugar. That's what it means, low or below for hypo. And so in this case, that's the prefix we use here. We're going to use hypo for ClO minus to say that we have fewer oxygens than chlorite. We say hypochlorite. And so ClO minus is the hypochlorite ion. Now, one thing you should note is oftentimes you'll see this written as OCl minus as well. They're totally interchangeable, totally equivalent, same thing either way. Cool. Once again, note that it ends with the ITE ending. And if you've already memorized these, then you can do the same thing when you translate these into the corresponding oxyacids, where you turn the ates into icks and the ites into us's. And so in this case, HClO3, the corresponding oxyanion of chlorate, is just plain old chloric acid. So, and then HClO2, the corresponding oxyacid of the chlorite ion, is chlorous acid. So down here, HClO4, the corresponding oxyacid of perchlorate ion, is perchloric acid. And then finally, HClO, which also might be seen written as HOCl, same diff, is the corresponding oxyacid of the hypochlorite ion, so it's hypochlorous acid. Cool, and you'd have the same analogous sets of 4 oxyacids for both bromine and iodine as well. So you'd have like hypobromous acid, bromic acid, perbromic acid, and you'd have hypoiodous acid, iodic acid, and periodic acid. And oddly enough, if you actually write out periodic acid, it's spelled exactly the same way as periodic. There's your chemistry trivia for the day. But that concludes us naming our acids here. We did binary, we did oxy, and you pretty much just got to get used to identifying these. And again, if you've already memorized your polyatomic ions, it will make your life so much easier when you get to this stage. So, but now we've named ionic compounds, we've named binary molecular compounds, and now 2 types of acids, binary acids and oxyacids. And once again, when you're doing a nomenclature in your general chemistry class, first thing you want to do is identify which of those 4 types of compounds you've got so that you know how to apply the right set of rules. Now, if you found this lesson helpful, give me a like and a share. Let's YouTube know to share this with other students who might equally find it helpful. And if you've got questions on anything we did here or anything related, feel free to leave them in the comment section below. And I just want to let you know that much of what I've put on the study guide here, the rules and things of that sort, and some of the examples, they're all also embedded on a playlist on my website along with the videos, nice collapsible menus, a lot of what's in the study guides, all there together. So I'll put the link for this particular lesson in the description below. And also want to just point out once again, my general chemistry master course, where on top of the videos and the study guides, I've got over 1,200 practice problems as it stands. I keep making more. Got final exam rapid reviews, chapter tests, practice final exams, lots of opportunity to put into practice what we've presented here. Free trial is available. Happy studying.